All right, so today we're diving into something pretty crucial in the world of AI, something called certified robustness for deep neural
Yeah.
networks. And we've got this research paper, so certified robustness for deep neural networks.
Okay.
And it's pretty dense.
Right.
But thankfully, our listeners are pretty deep into math and machine learning, data science.
Yeah, they can handle
So
it.
we can really kind of extract the good stuff here, right?
Absolutely.
So when we talk about certified robustness, what are we really getting at here?
I think what's really fascinating about this whole concept of certified robustness is it goes beyond just saying, okay, we've defended against these like known attacks.
Right.
It's about guaranteeing that a model can resist any attack
Wow.
within certain constraints, of course. So it's like instead of hoping for the best, it's
Yeah.
about having this provable security.
That's a big deal, right? Because we've all seen, I mean, in the news everywhere, how vulnerable these DNNs, deep neural networks, can be
Oh,
to
absolutely.
these adversarial attacks. I mean, we're talking tiny tweaks to the data that can
Right.
completely derail the model's predictions.
Yeah, it's wild. Like imagine a self-driving car misclassifying a stop sign just because someone slapped a tiny sticker on it.
Yeah.
The implications for safety are just enormous.
Huge. And that's where I guess the limitations of these kind of like empirical defenses come in, right? Where you're constantly,
Yeah, you're always playing catch up.
right, you're playing catch up with the latest attack.
Right, exactly. So certified robustness is about saying, okay, let's step back and build a mathematical framework that gives us guaranteed protection.
Okay, so how do we actually build this framework?
Yeah, so the paper lays out like two main paths you can take, two main approaches.
Hmm.
Robustness verification and robust training.
Okay.
And they kind of go hand in hand.
They work together.
Yeah, yeah. So verification is all about mathematically proving like a lower bound on the model's performance
Okay.
against any attack, right? So it's like saying, look, no matter what the attacker throws at it, we can guarantee that this model will perform at least this well.
I see. So it's that baseline level of performance.
Exactly.
No matter what you throw at it.
Right. But then, the paper gets into the different types of verification.
Yeah, I saw that.
You've got complete verification and incomplete verification.
Right.
Complete verification is really the ideal.
Okay.
It gives you absolute certainty. The problem is it's really computationally expensive and often just not practical for the really big complex models that we're working with these days.
So it's that trade-off then between.
It's always a trade-off, right? Accuracy versus scalability.
Yeah, so complete verification is like, I don't know, like doing a full body scan.
Okay, yeah.
And then incomplete is more like a targeted checkup.
Yeah, that's a good way to put it.
You're not getting the full picture.
Exactly. You're getting a quicker assessment.
Right, you're getting a faster
result.
Exactly.
Result.
But you might be missing something.
Okay, so then the paper dives into all these different verification techniques.
Well, yeah, it's a lot.
Solver-based methods, MIL-P, branch and bound. It's kind of overwhelming, to be honest.
It can be, but at their core, they're all trying to analyze how the model behaves and figure out some bounds on its performance under attack.
Right.
So like the solver-based methods, those are the runs where you basically translate the problem into these constraints that you can solve with logical tools.
Like a really complex Sudoku puzzle, but for AI.
Exactly. And then you've got MIL-P, which stands for mixed integer linear programming.
Right.
It's kind of like your classic optimization problem,
Okay.
but it's got this added twist of discrete elements.
So it's like you're trying to plan a delivery route, but each stop has like a really strict time window. Yeah. Yeah, that's a good example.
And then there's branch and bound, linear relaxation, multi-neuron relaxation, SDP. It's a lot to take in.
It is. But they're all essentially trying to find these clever ways to analyze the model and figure out, okay, how bad could things get under attack?
Right.
Branch and bound, that's the one where you systematically search for like the worst case scenario.
Okay.
It's like imagine you're navigating a maze and you're trying every path until you find the one that leads you to the worst possible outcome.
Okay, so it's very thorough.
Yeah, it's very systematic, very thorough.
And then you have linear relaxation and multi-neuron relaxation, which it sounds like they're kind of simplifying the problem a bit.
Yeah, they trade off some precision for speed, basically.
Okay.
It's like using a simplified map to navigate a city. It's easier to understand, but you might miss some of the smaller details.
Got it. So you gain speed, but you lose some of that accuracy.
Right, exactly.
And then there's SDP, which uses this powerful optimization framework.
Mm-hmm.
But it can be really computationally expensive.
It can be a bit heavy, yeah.
Okay. And then there's this whole other category of approaches
Right.
that look at the smoothness of the model's functions.
Yeah, the Lipschitz properties and curvature.
It's kind of like judging how far a ball will roll based on the steepness of a hill.
Right. That's a good analogy. If the model's functions are relatively smooth,
Yeah.
it's easier to set boundaries on how they'll behave, even under attack.
Okay, so we've got all these ways to verify robustness.
Right.
But what about, like, building that robustness into the model from the beginning?
Yeah, that's where robust training comes in.
Okay.
So instead of just testing for robustness, you're actually training the model to be robust from the ground up.
So it's like training a muscle. Yeah.
Exactly. You're making it inherently more resilient to those attacks.
And the paper talks about, like, 3 main categories of robust training.
Yeah, you've got regularization-based, relaxation-based, and augmentation-based.
Okay, break those down for me. What are the key differences there?
Sure. So regularization-based methods, they basically add these constraints during training to encourage certain properties in the model.
Like almost like a sculptor who's kind of subtly guiding the clay as they're working.
Yeah, that's a good way to think about it. Then you've got relaxation-based training.
Okay.
And this is where those same relaxation techniques we talked about for verification,
Right.
those can actually be used during training to directly guide the training process.
Okay, so instead of just testing for robustness,
Mm-hmm.
they're actually being used to build it in.
Right. Exactly.
And then augmentation-based, this is where you're introducing those adversarial examples.
Yeah, you're basically exposing the model to these carefully crafted adversarial examples during training.
Like a vaccine.
Exactly. It's like giving the model a vaccine so it learns to recognize and resist these attacks.
Okay, I'm starting to get a feel for this landscape now.
Good.
But the paper also, it really emphasized that, robust training is most effective when it's paired with a matching verification method.
Yeah, that's a key point.
So it's not enough to just pick, like, the best training method or the best verification method in isolation.
Right. It's all about finding the right combination, the right pairing.
Right. The right synergy between the two.
Exactly. And that's where this benchmarking section of the paper comes in, which is really, really fascinating.
Yeah, so they evaluated a whole bunch of different approaches on these standard data sets like MNIST, CIFAR-10, ImageNet.
Right, and they even created this open source toolbox so that other researchers can easily evaluate their own methods.
That's awesome.
Yeah, it's really great for standardizing the evaluation process.
Okay, so they put all these approaches head to head. What were some of the key findings there?
Well, one thing that really jumped out is for smaller models, complete verification was really the way to go. It gives you the highest level of certainty. But as the models get larger and more complex, those linear relaxation methods become much more practical.
So again, that trade-off between precision and scalability.
Right, exactly.
Yeah.
And in terms of robust training, it really made a big difference in the results, but only when it was paired with a matching verification method.
So it's like you need to have a well-coordinated team.
Yeah, they have to work together.
The training and verification.
Yeah.
Okay, were there any clear winners in terms of, like, specific data sets or specific types of attacks?
It really depended on the specific context. For example, on ImageNet, those probabilistic methods, the ones that inject randomness into the verification process,
Right.
those were the ones that really dominated. But they struggled with certain types of constraints.
Okay, so there's no one-size-fits-all solution.
No, it's really all about understanding the strength and limitations of each approach.
Yeah, and picking the right one for the job.
Exactly.
And the paper even includes, like, a flow chart
It does, yeah.
to help guide people in that process.
It's very helpful, actually.
Okay. But one thing that also stood out to me was that even with all this progress, certified accuracy, especially on those complex tasks, it still kind of lags behind what we see on like clean data, on data that hasn't been perturbed.
Yeah, that's true. We're not quite there yet.
Right. There's still work to be done.
But we're getting closer.
Okay, so we've covered a lot here.
We have.
From the basics of certified robustness
Yeah.
to a whole, like, a smorgasbord of verification and training techniques.
It's a lot to digest.
And I think what's clear is that there's this constant tension between, like, accuracy and scalability.
Always a trade-off.
Precision and efficiency.
Yeah.
And finding that that sweet spot.
Finding that balance.
That's really the key.
Exactly.
To making this whole certified robustness thing practical for the real world.
Absolutely. And that's what we're going to delve into next.
All right, so we're going to take a quick pause here to kind of let all this information sink in.
Yeah, good idea.
And when we come back, we'll unpack some of those practical implications and see how this research is really shaping the future of trustworthy AI.
Looking forward to it.
Yeah, me too.
Okay, so, we talked about all those verification techniques earlier.
Yeah, it was a pretty long list.
It is a long list, and I think it's helpful to maybe unpack a few of them a little bit more.
Yeah, let's dig into some of the specifics.
Right, so we talked about solver-based methods.
Right.
And how they can be really powerful.
Yeah, but they run into that scalability wall.
Exactly. So think of it this way. They're really great for small models, but as the model gets larger and more complex, the computational cost just explodes.
Okay.
It's like, trying to solve a Sudoku puzzle that's the size of a billboard.
Okay, yeah. That's a good visual.
Right. It just becomes intractable.
So that's where something like millipems in, right?
Right. Exactly. Millip or mixed integer linear programming.
Right.
It's a bit more efficient, especially for those medium-sized models.
Yeah.
And what's interesting is the paper highlights that Millip is even more effective when the model is specifically designed to be verifiable.
Oh, interesting.
It's like, if you're building a house and you design it with accessibility in mind from the beginning,
right,
it's much easier than trying to retrofit it later.
Yeah, you're not trying to shoehorn it in.
Exactly.
Yeah.
So there are these design choices you can make that can really improve the verifiability of the model.
Okay, so thinking about verifiability from the start.
Right, from the ground up.
Now, what about branch and bound?
Ah, yes. Branch and bound.
That seemed to be one of the most promising techniques, especially for those larger models.
It is a very powerful technique. So branch and bound, it essentially systematically explores all the possible on-off states of each neuron in the network.
Oh.
So it's like searching a maze, but
right,
but you're doing it intelligently. You're pruning branches that lead to dead ends.
So you're eliminating possibilities that are either guaranteed to be safe or guaranteed to be unsafe.
Exactly. You're ruling out those paths that you don't need to explore.
And that efficiency lets it handle models with hundreds of thousands of neurons.
Right. It can scale to quite large models. But of course, even branch and bound has its limitations.
Of course, nothing's perfect.
Right. So if you need extremely tight robustness guarantees, or if you're dealing with, truly massive models, you might run into some challenges.
So that's where those relaxation techniques come in.
Exactly. So we talked about linear relaxation, multi-neuron relaxation, SDP.
Right.
These are all approaches that essentially simplify the problem to make it more manageable.
So it's a trade-off then, right?
It is. You're trading off some precision for speed. It's like using a simplified map to navigate a city.
Right.
It's easier to understand, but you might miss some of the side streets, the smaller details.
Okay, so you're getting the big picture.
Right. You're getting the big picture.
Definitely not all the nuances.
Right, exactly. So with linear relaxation, for example, you're approximating these complex relationships with simpler ones. And there are methods like interval bound propagation, which are incredibly fast and scalable.
Yep. Yeah.
But they can be quite loose in terms of the guarantees they provide.
So again, that trade-off between speed
and precision.
Precision. Yeah. And then there's multi-neuron relaxation, which takes it a step further and considers groups of neurons together.
Right. And that gives you tighter bounds.
Okay.
But it also, adds some computational cost.
Of course.
And then you've got SDP, semi-definite programming, which offers this really powerful framework for optimization, but it can be quite computationally demanding.
It sounds like there's this whole spectrum of relaxation techniques.
There is, yeah.
And they all kind of have their sweet spot in terms of scalability and precision.
Exactly. It's about finding the right tool for the job, right?
Right. Now, we can't forget about those approaches that look at the Lipschitz properties and curvature.
Oh, yes, those are important too. So instead of focusing on individual neurons, these methods look at the smoothness of the model's functions.
Right, like that hill analogy we talked about earlier.
Exactly. If the model's functions are relatively smooth, it's easier to set bounds on how they'll behave, even under attack.
It's like adding shock absorbers to the model.
Yeah, that's a great way to think about it.
Okay, so we've got those methods. Now, what about probabilistic verification?
Ah, yes. probabilistic verification. This is where we start to introduce randomness into the process.
Okay, this is the randomized smoothing technique, right?
Exactly, randomized smoothing. So the idea here is you add noise to the input data. And by analyzing the model's behavior over a distribution of these noisy inputs, you can effectively smooth out its decision boundaries and make it less susceptible to those tiny, carefully crafted adversarial perturbations.
So those little tweaks that the attackers rely on are less effective because they're getting drowned out by the noise.
Exactly. It's like, you're adding this layer of fuzziness to protect the model.
Right, right. And the cool thing is you can apply this to pretty much any model architecture.
Yeah, it's very versatile.
But choosing the right type of noise is important, right?
It is. It is. So, for example, Gaussian noise works well for small perturbations, whereas Laplacian noise is better for attacks that target like a few specific input values.
So it's like choosing the right type of camouflage depending on the terrain.
Yeah, that's a good analogy. But of course, even with the perfect noise, probabilistic verification doesn't give you those absolute guarantees.
Right. It's probabilistic.
Exactly. It's telling you, okay, with high probability, the model will behave this way, but there's always that small chance that an adversarial example might slip through.
So it's a trade-off again.
It is.
We gain scalability.
Yeah.
We gain the ability to handle these complex models, but we lose some of that absolute certainty.
Right. And it's worth noting that probabilistic methods still struggle with certain types of attacks, particularly those attacks in the L-infinity norm.
Right. And that's an area of ongoing research, I guess.
It is, yeah. But even with those limitations, randomized smoothing has really been a game changer for the field.
Okay.
It's allowed us to tackle models that were previously just out of reach.
So we've explored the two main branches of certified robustness, verification, and robust training. And we've gone through this whole array of techniques for both.
The whole toolbox.
And I think the main takeaway here is that there's no single best approach.
Right. It's not a one-size-fits-all situation.
You really have to understand the strengths and limitations of each technique.
Exactly.
And choose the right combination for your specific needs.
And for your specific model, your specific data.
Right. It's about finding that perfect pairing.
That synergy.
That synergy between the training and the verification methods.
Exactly.
Okay. So before we jump into the practical implications of all this, I think it's worth taking a moment to just kind of reflect on what we've learned so far. Okay, so wow, a lot to process here on certified robustness. We've gone from like the fundamental ideas to all these different techniques.
Yeah, it's a whole world in itself.
And I feel like we're just scratching the surface.
Yeah, I mean, one thing that strikes me is just how quickly this field is evolving,
Oh, absolutely.
It wasn't that long ago that, trying to certify robustness for anything beyond these like toy models was a huge challenge.
Right.
And now we're seeing techniques that can handle models with like millions of parameters.
That's incredible, yeah.
It's really remarkable progress.
But as you said before, we're not quite at the finish line yet.
No, definitely not.
Especially when it comes to certified accuracy on those more complex tasks.
Right.
We're still kind of lagging behind what we see on clean data.
That's true, but I think it's important to acknowledge how far we've come, right?
Oh, for sure, for sure.
The research in this paper, I mean, it really showcases some groundbreaking approaches.
Yeah, and that benchmarking effort, I mean,
benchmarking is so valuable.
Yeah, it really highlights how important it is to choose the right combination of techniques.
Absolutely. It's not just about finding like the best verification method or the best robust training method in isolation, right?
Right.
It's about understanding how those methods interact and choosing a pair that really complements each other.
Like that one example in the paper where they show that that one robust training technique actually hurt performance.
Right. It actually made things worse.
When it was paired with the wrong verification method.
Exactly. It just shows that we need to take this more holistic approach.
Yeah.
We need to think about the entire pipeline.
Right, from model design.
Model design, training, verification, deployment, the whole thing.
So this isn't just a theoretical pursuit anymore.
No, not at all.
This is about like building practical tools and workflows
that can actually be used in the real world.
And I think for researchers like you and our listeners,
yeah,
this paper really provides like a roadmap for future exploration.
It lays out the challenges, the open questions, the directions that we need to to go in.
Yeah, and there are still so many open questions,
Oh, yeah. So.
especially around handling those L infinity norm attacks
Right. That's a big one.
and scaling these techniques to even larger models.
Right. Pushing the boundaries.
But that's where the excitement is, right?
That's what keeps us going, right?
To keep pushing the limits of what's possible.
To build these AI systems that are not just powerful, but also incredibly robust and reliable.
And I think, one thing that I'm particularly intrigued by is the potential for robust training to really bridge that gap between certified accuracy and clean accuracy.
Oh, yeah, that's a really exciting prospect.
The paper even suggests that with further breakthroughs in robust training techniques, we might one day achieve certified robustness that's on par with what we see on clean data.
That would be a game changer.
It would be a whole new world.
Think about it. We could deploy deep neural networks in these safety-critical applications with absolute confidence, knowing that they'll perform reliably, even under attack.
That's a future worth striving for.
It is. So to our listeners, I encourage you, dive into this paper, explore this world of certified robustness.
Yeah, it's a challenging field.
It is, but it's also incredibly rewarding. And the work that's being done here, it has the potential to really revolutionize the way we build and deploy AI systems.
Absolutely. Well, this deep dive has been, I'll be honest, a bit of a mind bender for me.
Yeah, it's a lot to take in.
But in a good way.
In a good way, yeah.
It's definitely sparked my curiosity, and I hope it's done the same for you, our listeners.
Stay curious, everyone.
Stay curious as always. And we'll see you next time for another deep dive into the world of cutting-edge research.